Hello friends, I welcome you in lecture number 13 on complex differentiation. In this lecture also we will discuss two functions for their analyticity. We have discussed in earlier lecture the definition of entire function, and entire function is that function which is analytic at every point, or we can say that a function which is analytic everywhere is called entire function. So whenever they ask to prove that given function is entire function, all we have to prove is that given function is analytic at every point. So we try to prove that this function is entire, that is it is analytic at every point, and it is already given with its real and imaginary parts. So we can compare this with u plus iv, and we can write its real and imaginary parts. Suppose this is equal to say u plus iv, then u equal to, if we compare this with u plus iv, u is e raised to minus y times sin x, and v equal to minus e raised to minus y times cos x. And as we know, first we have to find out first order partial derivatives of u and v with respect to x and y. Here we differentiate with respect to x, therefore e raised to minus y is constant, derivative of sin x is cos x. And when we differentiate with respect to y, we consider sin x as constant, and derivative of e raised to minus y with respect to y is minus e raised to minus y, and sin x as it is. Similarly here, if we differentiate with respect to x, we have minus e raised to minus y considered as constant, derivative of cos x is minus sin x, therefore we have negative negative positive, and we have e raised to minus y times sin x. And when we differentiate with respect to y, this is constant, derivative of e raised to minus y is minus e raised to minus y, and minus minus plus, so here we have e raised to minus y cos x as it is. And then we check that at which points CR equations are satisfied. We know that CR equations are del u by del x equal to del v by del y, and del u by del y is minus del v by del x. So if we observe these two functions, here del u by del x is e raised to minus y cos x at any point xy, and del v by del y is also e raised to minus y cos x at any point xy. That means this equation is satisfied at all points z equal to ordered pair xy in the complex plane. Then what is del u by del y? It is minus e raised to minus y sin x. Del v by del x is e raised to minus y sin x. Therefore, minus vx is minus e raised to minus y sin x. And if we compare these two, we can see they are same, minus e raised to minus y sin x. This means del u by del y and minus del v by del x are also same or equal at any point z equal to ordered pair xy. This means both CR equations are satisfied at every point in the complex plane. So we can write directly both CR equations are satisfied at every point in the complex plane. At every point, say z equal to ordered pair xy in the complex plane. After that, we have to check the continuity of first order partial derivatives of u and v, and if we observe, these first order partial derivatives contains the trigonometric functions sin x cos x and exponential functions, and we know that sin x, cos x, exponential are always continuous at every point, therefore they are obviously continuous at every point z equal to xy. Clearly del u by del x, del u by del y, let me write here del u by del x, del u by del y, del v by del x and del v by del y are continuous at every point z equal to ordered pair xy in the complex plane. So we should write systematically all these things so that we can get full marks. So here we have seen that both conditions for differentiability are satisfied, therefore we can say that f of z is differentiable at every point or differentiable everywhere. And we know that if function is differentiable everywhere, then it is analytic everywhere. Therefore f of z is analytic everywhere, and the function which is analytic everywhere is entire function. Therefore f of z is entire function. So if you have observed in all the previous lectures and in this lecture also, we are just concentrating on the satisfaction of Cauchy-Riemann equations. If we know that how to check whether CR equations are satisfied or not, then we can check the differentiability, we can check the analyticity, as well as we can show that given function is entire function. So all you have to remember is that you must find out the points in the complex plane at which both CR equations are satisfied. And continuity condition is easy. You can look at the first order partial derivatives and you can check whether they are continuous or not. After that you can remember the definition of analytic function, or you can remember all these things, that function which is differentiable everywhere is always analytic everywhere. So whenever your function is differentiable everywhere, you can directly write that it is analytic everywhere. Similarly, if your function is nowhere differentiable, then it is nowhere analytic. And if your function is differentiable at finite number of points only, differentiable at finite number of points only, then also it is nowhere analytic. So these are the simple remarks that will be helpful for checking the analyticity of a given function. We have discussed in earlier lectures that if we consider f of z equal to z bar, then it is nowhere differentiable. That means z bar is nowhere analytic. If you recall, we have shown that this function mod z square is differentiable at only one point, which is origin. Therefore this mod z square is nowhere analytic. Similarly, we have shown that these two functions, z into imaginary part of z and z into real part of z, are also differentiable at origin only. Therefore these two are also nowhere analytic. So using these three simple remarks, you will be able to decide or determine the number of points at which given function is analytic. So all you have to remember is that first we have to find out the number of points at which CR equations are satisfied, and the points at which CR equations are not satisfied, function is never differentiable at those points, and therefore it is never analytic at those points. All we have to concentrate is at those points where function is satisfying Cauchy-Riemann equations, or real and imaginary parts of function satisfy Cauchy-Riemann equations. So this is very easy. You can easily check whether given function is entire or analytic or differentiable, or you can check the Cauchy-Riemann equations. I have taken one more example here. Check the analyticity of this function. It is already given with its real and imaginary parts. So suppose we compare with u plus iv, then we have u equal to 3x plus y and v is 3y minus x. Now I will find out first order partial derivatives. Del u by del x is derivative of 3x with respect to x is 3. Here derivative of y is 0 because we consider y as constant while differentiating with respect to x. Del u by del y. So while differentiating with respect to x, this becomes constant and derivative of y is 1. Here also when we differentiate with respect to x, this is constant, therefore its derivative is 0 and minus derivative of x is 1. And del v by del y is derivative of 3y is 3 and derivative of x is 0. And here also you can see del u by del x is 3 at any point, del v by del y is also 3 at any point. And if we consider negative sign here minus vx, then we will have plus 1. So uy and minus vx are also equal at every point. So this means clearly these equations are satisfied. Del u by del x equal to del v by del y, and del u by del y is minus del v by del x at every point z equal to xy in the complex plane. And all these first order partial derivatives are constants, therefore they are obviously continuous. We know that constant function is always continuous, so that also we have to write. Also all these first order partial derivatives are continuous at every point z equal to ordered pair xy in the complex plane. So both the conditions for differentiability are satisfied. So we can write that f of z is differentiable at every point, or we can simply write f of z is differentiable everywhere. And we know that if function is differentiable everywhere, then it is analytic everywhere. Therefore f of z is analytic everywhere, and function which is analytic everywhere is entire function. So this is another example of entire function, but here we are just asked to check the analyticity of this function. So we stop here that function is analytic everywhere. So now I hope you are clear about determination of differentiable function or analytic function or entire function. So I think this type of examples are enough, and in next lecture we will discuss another things related to this topic of complex differentiation. Thanks for watching.